Hello everyone, welcome to the HPL seminar this week. It is my pleasure to introduce today's speaker, Sasa Cigoja. Sasa started his undergraduate in 2012 at the University of Applied Science Technicum Vienna, specialized in sports engineering. During his undergraduate, he worked on quantifying biomechanical effects of wearing a sacroiliac belt, and he achieved a bachelor's degree in engineering in 2015. Then he came to the University of Calgary in 2016 and started his master's course under the supervision of both Drs. Benno Nick and Brent Edwards. During his master's, he found himself wanting to do a PhD as well, so he decided to do a fast-track PhD degree in 2018. For his thesis, Sasa has been primarily working on shoe bending stiffness and the mechanics of muscle tendon units in running, and he is planning to graduate this year. Aside from his academic background, he did an internship at Adidas in 2016, performing testing apparel products across various sports. Also, he visited the lab of Drs. Andy Cresswell and Luke Kelly at the University of Queensland, Australia, and worked on a project of estimating arch mechanics and plantar muscle tendon unit behavior in running. And all of these experiences have become a strong motivation for him to further investigate why shoe with stiffening elements can improve running performance. Currently, he has been focusing on preparation for his thesis defense in next month, and very much excited to see about what would come next afterward. When I asked him about interesting or fun facts of himself, he wanted to share one of his experiences that he got when he was in Australia as a visiting student. So Sasha went to Steve Irwin's zoo with some people from the lab that he visited. And at the zoo, there is an area where kangaroos were moving and jumping freely. And you could go enter the area and feed and pet the kangaroos. So most people were feeding the kangaroos when they were petting them, but Sasha was not actually giving any food when he was petting them. Then he found one of kangaroos was not actually happy with that. So the kangaroo started boxing and kicking him with its hind legs while keeping the balance on its tail. So whoever goes to the zoo, please make sure you feed them really well. Today, he will be giving a talk entitled as Shoe Bending Stiffness and Muscle Tendon Unit Function in Running. Whenever you're ready.
Thank you, Sungwon. In 1997, Stefanishin and Nig published a study where they investigated the relative contribution of the metatarsophalangeal joint to total lower limb joint work. The surprising finding at that time was the fact that the MTP joint was mainly dorsiflexed during the stance phase of running. This was different compared to the other lower limb joints, as they typically first undergo flexion and then extension. Here on the right-hand side, we have the MTP joint moment on the top and MTP joint power on the bottom or the stance phase of running. And we can see on the top that the MTP joint predominantly experiences a plantar flexion moment across the stance phase. But because the joint is mainly in a dorsiflex position, the flexion moment resulted in negative power. So you can see here on the bottom how the MTP joint power is predominantly negative over the stance phase. This means that mechanical energy was absorbed at the joint. And this eccentric work performed at the MTP joint was speculated to potentially be disadvantageous for athletic performance. It was therefore hypothesized that if the stabilizing function of the MTP joint could be maintained without the large amounts of energy lost, performance benefits could potentially be observed. One way to limit the extension of the MTP joint was to stiffen footwear in longitudinal direction by inserting carbon fiber plates along the full length of a shoe. And Stefanishyn and Nig were the first to investigate the effects of increased bending stiffness on biomechanical variables and performance. Here on the right-hand side, we can see the metatarsal angle over the stance phase of running, and on the bottom again, the metatarsal power over the stance phase for 3 shoe conditions. So the black line represents the control shoe, the dashed line represents a stiff shoe condition, and then the dotted line represents a very stiff condition. And on the top, we can see that the MTP joint showed less dorsiflexion towards the end of stance, this part, when running in a plated shoe condition. Similarly, the negative MTP joint power was lower, and therefore less negative work was absorbed when running in shoes with increased bending stiffness. The authors also showed that jump height was increased in the stiff condition when jumping or when performing a jump with a run-up. It was unknown, however, if similar changes in performance would be observed in running. In 2004, Stefanishyn and Fusco investigated how sprint performance was affected when carbon fiber plates of different stiffnesses were inserted in sprinting spikes. The findings of this study show that at first, sprint times were reduced with increased bending stiffness. However, when the stiffness of the plates was increased even further, the performance benefits were reversed and sprint times increased again. More importantly, the level of midsole bending stiffness that resulted in best performance varied between participants. So you can see here on the top for subject A, the condition that resulted in the lowest sprint time and therefore best performance was this condition here, whereas for subject B, the best condition was this one. This subject-specific optimal or quote-unquote optimal stiffness was not related to simple anthropometric characteristics such as mass, height, or shoe size. Instead, the author speculated that individual strength, force length, and force velocity relationships of the ankle plantar flexor muscles could be related to the level of stiffness that allows athletes to perform best. The first study to investigate the rate of oxygen consumption, or VO2, while running in footwear with varying bending stiffnesses was performed by Roy and Stefanishyn in 2006. Here on the top, we can see that compared to running in a control shoe, which is illustrated by this data point, VO2 decreased when running in the stiff shoe by approximately 1%. However, when stiffness was increased even further, VO2 increased again, and there were no differences compared to the control shoe. This suggested that a U-shaped relationship between shoe bending stiffness and VO2 exists. The authors also reported that body mass was correlated with VO2 variations relative to the control shoe. That means that runners with a greater body mass had larger metabolic savings when running in a stiff shoe. This relationship, however, was not significant in the stiffest condition anymore. Although increased negative ankle joint work was observed in the stiffest condition, as can be seen here, there were no differences in muscle activity between shoe conditions. The authors acknowledged that the underlying mechanisms linked to improved running economy may not be fully understood. However, they speculated that the optimal bending stiffness could be related to body mass. We cannot talk about bending stiffness of footwear and running performance without talking about this shoe, the Nike Zoom Vaporfly 4%. At the time of its release, the Vaporfly shoe differed in 2 major characteristics from other running footwear, namely a highly resilient midsole material that was suggested to be able to return up to 87% of the energy stored during a step. For comparison, the marathon world record shoe at that time was supposed to be able to return about 11% less than that. And the second major characteristic was a curved carbon fiber plate, illustrated here by this black line, which increased the longitudinal bending stiffness of the shoe by about 165% compared to the world record shoe. Since its release, running in the Vaporfly or shoes containing highly resilient midsole material and curved stiffening elements resulted in many world records in long distance running competitions and in the first run over a marathon distance in under 2 hours. The first two studies that investigated the physiological and biomechanical effects of running in Vaporfly shoes were performed by Hochhammer and colleagues. The authors compared the Vaporfly, which at that time was a prototype shoe, with the Adidas Adizero Adios Boost, which was the world record shoe, and another racing flat. On the right-hand side, we have the energetic cost of running at 3 different speeds for the racing flat NS, the world record shoe AB, and the prototype Vaporfly shoe NP. Each gray line represents one runner, and the group means are represented by the colored circles. It should maybe be noted that the full lines may suggest a dependence between shoe conditions, which is not really true. The lines are just supposed to help visualizing the individual responses of the runners. The authors showed that running in the Vaporfly reduced the energetic cost of running by approximately 4% on average compared to the world record shoe. A biomechanical analysis showed that the negative MTP and ankle joint work was significantly decreased when running in the Vaporfly. Hochhammer and colleagues also calculated that the compressive work rate due to the resilient midsole material was approximately 50 times greater than the bending work rate due to the curved carbon fiber plate. The authors therefore concluded that the performance benefits were more likely due to the energy return properties of the midsole material rather than the carbon fiber plate. 2 additional studies followed up and independently investigated the running economy improvements in the Vaporfly compared to other running footwear. A study performed by Hunter et al. Showed that the Vaporfly shoe improved running economy by 2.8% on average compared to the world record shoe. The authors also found a significant relationship between stance times and metabolic benefits in the Vaporfly. Another study performed by Barnes and Kilding, shown here on the right, found that running economy improved by 4.2% in the Vaporfly shoe, which is illustrated here by this blue mean, compared to the world record shoe here in the purple mean. The authors also showed that longer stance times were related to greater benefits in the Vaporfly shoes. Although the underlying sources behind the metabolic benefits when running in footwear with straight carbon fiber plates are not perfectly understood, some mechanisms were introduced in the past. The principle of minimizing energy loss suggests that athletic performance can be improved by decreasing the eccentric work performed by muscles. The first study that looked into the effects of bending stiffness on running biomechanics and jumping performance, performed by Stefanition and Nig, showed that the MTP joint predominantly performed negative work or absorbed mechanical energy, which is shown here on this graph. However, when the stiffness of the shoe was increased from control on the black line to very stiff, the dotted line, the amount of negative power and therefore the amount of energy that was absorbed was reduced. But when the increase in potential energy during jumping in the stiff shoe, which is plotted here on the y-axis, was related to the reduction in MTP energy here on the x-axis, no one-to-one relationship was observed. This suggested that the principle of minimizing energy loss is likely not the sole underlying mechanism behind these performance improvements. The principle of storing and returning energy suggests that elastic energy could be stored in carbon fiber plates as the MTP joint undergoes extension. Then some of this energy was hypothesized to be returned during subsequent joint flexion. Here we have a study by Willwacher et al. Who compared the metatarsal joint power, shown on the y-axis, over the stance phase of running for 3 shoe conditions. The control shoe is illustrated by the dashed line, A stiff condition is illustrated by the gray line, and then a very stiff condition in the black line. The area under the positive power curve, which is the positive work at the MTP joint, was smaller in the control condition. So this would be the area between the dashed line and the horizontal. And this area was smaller compared to the area between the gray line and the horizontal, or the black line and the horizontal. The stiffer the shoes, the more positive work was performed. The authors interpreted this as a reutilization of elastic energy stored in the plates. However, because other studies show that even further increases in bending stiffness did not result in even greater running economy improvements, it seemed unlikely that the principle of energy storage and return was the sole mechanism. The principle of improved muscle function suggests that athletic performance can be increased when muscles operate on a more favorable position on their force length or force velocity relationship. This was suggested to occur by changing the gear ratio. The gear ratio is the ratio between the external and internal moment arm. The external moment arm is determined as the perpendicular distance between the ground reaction force vector, illustrated with this arrow, and the ankle joint center. And the internal moment arm is determined as the perpendicular distance between the muscle tendon unit force and the ankle joint center. A study by Willwacher et al., shown here on the right, investigated how this external moment arm at the ankle joint on the y-axis was altered by increasing the bending stiffness of shoes, and is shown here for the second half of stance phase. The control condition is illustrated in the dashed line, the medium stiff condition by the black circles, and the high stiff condition with the white circles. The authors show that the external moment arm to the ankle joint centers increased with stiffer and stiffer shoes. Therefore, with a relatively constant internal moment arm, the stiffer shoes would result in a greater gear ratio. These changes in gear ratio were speculated to be related to changes in force generating capacities of the ankle plantar flexor muscle. Previous studies have shown that increasing the midsole bending stiffness of shoes can improve running economy. It can increase the external moment arm by translating the center of pressure further anteriorly during push-off. It can reduce the negative and increase the positive work performed at the MTP joint. It can reduce ankle plantar flexion velocities, and it can increase stance times. Several mechanisms were introduced attempting to explain the performance benefits observed when running in footwear with increased bending stiffness. One of these mechanisms, namely the principle of improved muscle function, is currently not well understood. Specifically, it is unknown if and how muscle function can be affected by the bending stiffness of running shoes. Therefore, the aims of my thesis were to primarily address the principle of improved muscle function. The first aim of the thesis was to investigate if lower limb joint work can be redistributed in stiffer shoes, and if this redistribution can be affected during a prolonged run. This was supposed to aid in understanding how muscle tendon units generate and absorb mechanical energy. The second aim of the thesis was to investigate how the function of the ankle plantar flexor muscles and muscle tendon units is affected by the bending stiffness. This was supposed to advance our understanding of potentially improved muscle function when running in stiff footwear. In 2018, Sana and colleagues investigated the joint-specific contributions to total lower limb joint work during a prolonged run. For this, they had participants run for 10 kilometers at a speed that was 5% slower than the individual season best time. Their main findings were that the positive ankle joint work decreased significantly over the course of the 10-kilometer run, illustrated here by the green triangles. They also showed that the positive knee and hip joint work increased compared to the beginning of the run with increasing running distance. However, only the positive knee work was significant, illustrated by the blue circles. The authors concluded that there was a redistribution of lower limb joint work from distal to proximal joints with increasing running distance. A footwear feature that has been shown to be able to affect mechanical joint work during running is the midsole bending stiffness. However, it was unknown if joint work redistribution, potentially in the opposite direction as reported here by Sano et al., could be induced by running in stiff footwear. For this reason, the purpose of a study that we published last year was to investigate if joint work redistribution could be introduced by increasing the bending stiffness of shoes. There, we had 13 participants run at 3.5 meters per second for 30 seconds in a control and a stiff shoe. On the left-hand side, we have the joint-specific positive work relative to total lower limb positive work. And on the right-hand side, we have the joint-specific negative work relative to the total lower limb negative work. The white bars represent the control condition and the pattern bars represent the stiff condition. We found that compared to control, running in a stiff shoe resulted in significantly more positive MTP joint work and significantly less positive knee joint work. We also found a significant decrease in negative MTP joint work when running in the stiff shoe condition. We interpreted the increase in positive MTP work and decrease in positive knee work as a redistribution from proximal to distal joints when running in a stiff shoe. This is a redistribution in opposite direction to what was reported by Sano et al. To occur due to prolonged running. Therefore, the purpose of the first study that I'll present today was to investigate if running in stiff shoes can affect the onset of lower limb joint work redistribution from distal to proximal joints during a prolonged run. Our hypothesis was that running in a stiff shoe will delay the onset of joint work redistribution during a 10-kilometer run. For this, we recruited 15 male trained runners who were able to run 10 kilometers in under 44 minutes. The testing consisted of 3 sessions, where on the first day, participants performed an incremental treadmill run to determine the individual speed at lactate threshold. On days 2 and 3, participants ran for 10 kilometers on a treadmill at 90% of individual speed at lactate threshold. 2 shoe conditions were used in this study. The control shoe consisted of a Nike Free 2018 model, and the stiff condition was achieved by inserting straight carbon fiber plates along the full length of the control shoe. The order of conditions between day 2 and day 3 were balanced randomized so that 7 participants first ran in the control and 8 participants first ran in the stiff condition. The stiff shoe varied between participants so that for 7 runners, the stiff shoe was about 4 times stiffer than the control, and for 8 runners, the stiff shoe was about 8 times stiffer than the control. Lower limb joint kinematics and kinetics were acquired using a 3D motion capture system and an instrumented treadmill. Baseline data was measured immediately after a 2-minute familiarization period and then subsequently every 500 meters. And the main outcome variable was the positive mechanical lower limb joint work. Here we have the positive MTP work relative to total lower limb joint work over the entire distance of the 10-kilometer run. Blue squares represent the means across the 15 participants in the control condition, and the red triangles represent the means of the 15 runners in stiff condition. And on the right-hand side, we have a table with the relative joint work at baseline, which is 0 kilometers, and the end of the run, which is 10 kilometers for the control and the stiff shoe. The asterisk represents significant differences compared to baseline at 0 kilometers. We can see that generally positive MTP joint work decreased with increasing running distance. In the control condition, MTP joint work decreased significantly at kilometers 9 and 10 compared to baseline. In the stiff condition, however, the mean decrease in MTP joint work at the end of the run was not significantly different from baseline. On the left-hand side, we have the positive ankle joint work relative to total lower limb work, again across the entire distance of 10 kilometers. And on the right-hand side, we have the respective values at kilometers 0 and 10 for both shoe conditions. Generally, positive ankle joint work decreased in both shoe conditions with increasing running distance. However, the point in time when ankle work was significantly different from baseline was 5 or 7 kilometers for the control shoe and 8 kilometers in the stiff shoe condition. Here on the left-hand side, we have the positive knee joint work relative to total lower limb joint work over the entire distance of the 10 kilometers. And we can see that knee joint work generally increased with progressing running distance for both shoe conditions. But in the control shoe, the first time that knee joint work was significantly different from baseline was at 5.5 kilometers, whereas in the stiff shoe condition, this first occurred at 7.5 kilometers. And then lastly, there was no significant difference in positive hip joint work between time points. The results of our study confirmed previously reported findings that show that prolonged running at near maximum effort redistributes positive lower limb joint work from distal to proximal joints. Compared to the beginning of the run, we found a significant decrease in positive ankle joint work of 5.1%. We also found that after running for 10 kilometers, positive knee joint work increased significantly by 4.7%. There was a reduction in positive MTP joint work of 0.7% and an increase in hip joint work of 1.1%. However, these changes were not significantly different to baseline. This confirms previous findings by Sano et al., who suggested that a redistribution of positive work from distal to proximal joints could be disadvantageous for two reasons. First, under the assumption that tendons are able to store and return relevant amounts of energy, a redistribution towards more proximal joints would mean that less energy is returned by distal tendons, predominantly the Achilles tendon. And because tendons of more proximal muscles, for example, the quadriceps, are thought to be less equipped for energy return, this would suggest that then the muscles would need to perform this additional work. And second, proximal muscle groups, for example, the quadriceps, have been shown to have greater muscle volume compared to distal muscle groups, for example, the triceps surae. Active muscle volume has been shown to explain the majority of changes in the energy cost of running at various speeds. Therefore, it may be possible that performing more work at proximal muscle groups would require greater active muscle volume and therefore increase the energy cost of running. We interpreted the findings that ankle joint work decreased and knee joint work increased at a later time point in the stiff compared to the control shoe as a delayed onset of joint work redistribution. We think that delaying the onset of redistribution by running in stiffer footwear may allow mechanical work to be performed at the ankle joint for a longer period during a prolonged run. This may keep the active muscle volume more similar to the state at the beginning of the run. And we think that this could mitigate steady increases in the energy cost of running typically observed during prolonged runs. The second aim of the thesis was to investigate if and how the function of the ankle plantar flexor muscles and muscle tendon units can be affected during running by increasing the bending stiffness of shoes. In 2014, Willwacher et al. Investigated how the ground reaction force levers can be affected during running by increasing the bending stiffness of shoes. On the left-hand side, we have a schematic that shows how the authors determine the ground reaction force levers. These levers were determined as the perpendicular distance between the ground reaction force vector, illustrated by this arrow, and the respective joint centers. On the right-hand side, we have the levers for 4 lower limb joints over the second half of stance during running in 3 shoe conditions. The control shoe is illustrated by the dashed line, the medium stiff shoe by the black circles, and the high stiff shoe by the white circles. The authors showed that generally the ground reaction force levers were increased towards the end of stance when running in stiffer and stiffer footwear. The effects were greatest at the metatarsophalangeal joint and at the ankle joint. These changes in ground reaction force lever were speculated to increase the gear ratio as the internal moment arms around joints were assumed to be fairly constant during the stance phase of running. Takahashi et al. Investigated how the gear ratio was affected during walking when people were introduced to differently stiff shoes. Here we have the gear ratio on the vertical axis over the stance phase of walking across a variety of conditions. So the barefoot condition, which is the most compliant one, is illustrated by the gray line, the shot condition by the black line, and then the differently stiff shoe conditions in the colored lines. Generally, by increasing the stiffness of the shoes, the gear ratio towards the end of stance phase was increased. And here on the right-hand side, we have the peak gear ratio and the average gear ratio for the 5 shoe conditions. And we can see that the gear ratio was significantly increased in the stiffest condition compared to the other shoe conditions. These results were different to what was previously speculated to occur during running, because the soleus muscle fascicle velocities were reduced when walking in stiff shoe conditions. However, the metabolic cost was significantly increased by about 11%. This suggested that there may be different mechanisms at play between walking and running. We performed a study last year where we investigated how the shortening velocity of a shank muscle tendon unit was affected by the bending stiffness of shoes. This shank muscle tendon unit was an estimation of the triceps surae and the Achilles tendon. And here on the graph, we can see the shank muscle tendon unit velocity on the vertical axis over the stance phase of running on the horizontal axis for 2 shoe conditions. The blue curve represents the control shoe, and the red curve, the stiff shoe condition. Negative values represent muscle tendon unit shortening. Our findings show that estimated peak muscle tendon unit shortening velocity was significantly reduced in the stiff shoe condition here at the end of stance phase. And we found that this likely occurred due to increased stance times when running in stiff footwear. However, due to the methods that we used, we were not able to distinguish whether the changes in shortening velocity could be attributed to the muscle or the tendon of the muscle tendon unit. For this reason, we performed a study with the purpose to investigate if gastrocnemius medialis muscle function in form of total fascicle shortening and average fascicle shortening velocity during stance can be affected by changing the midsole bending stiffness of running shoes. A secondary purpose was to estimate muscle fascicle work and Achilles tendon energy return while running in differently stiff shoes. Our first hypothesis was that total gastrocnemius medialis muscle fascicle shortening will not differ between stiffness conditions, as previous studies have not shown differences in ankle joint angles during running. Our second hypothesis was that increased stiffness will reduce average fascicle shortening velocities due to increased stance times. And lastly, we hypothesized that Achilles tendon energy return will not differ between stiffness conditions. For this, we recruited 17 male trained runners who were able to run 10 kilometers in under 44 minutes. The data collection consisted of 2 testing days. On day 1, participants performed an incremental treadmill run to determine the individual speed at lactic threshold. On the second day, participants performed 4 9-minute long runs, where the first 3 minutes were ran at 3 meters per second to get familiarized to the shoe condition. Immediately after the familiarization, speed was increased to 90% of individual speed at lactic threshold for another 6 minutes. The control condition consisted of a Nike Free 2018 model, and the stiff conditions were achieved by inserting different straight carbon fiber plates along the full length of the control shoe. We recorded right gastrocnemius medialis muscle fascicle images using an ultrasound system. The energy cost of running was determined using a metabolic cart, and lower limb joint kinematics and kinetics were measured using a 3D motion capture system and an instrumented treadmill. The ultrasound, kinematic, and kinetic data were recorded with the beginning of the final minute of each run for approximately 20 seconds, whereas the oxygen uptake was collected throughout the entire run. On the left-hand side, we have an exemplary image of a participant running on the treadmill. And you can see on the top, the mask that was used to collect oxygen uptake and carbon dioxide production. And on the bottom, you can see the ultrasound probe that was secured to the right gastroc muscle. On the right-hand side, we have an exemplary image of the ultrasound recordings, where on the top we have the ultrasound probe. On the left side, we have the proximal end of the probe. This is closer to the knee joint. And then on the right-hand side, we have the distal end of the probe closer to the ankle joint. These 2 lines here on the top and here in the middle represent the superficial and the deep aponeurosis. This yellow frame represents the region of interest, which in our case is the gastroc medialis muscle. This red line represents a muscle fascicle, and the pennation angle was determined between the muscle fascicle and the deep aponeurosis. The ultrasound images were processed using a semi-automated tracking software developed by Lichtwork and Ferris. On the left-hand side, we have the change in fascicle length relative to the length at heel strike over the stance phase of running for the 4 shoe conditions. The blue line represents the control shoe, the purple line, the stiff shoe, the green line, the stiffer shoe, and the red line, the stiffest shoe. Each line represents the mean across 14 participants, as ultrasound data for 3 runners had to be excluded due to insufficient quality. And on the right-hand side, we have the total fascicle shortening over the stance phase. The total fascicle shortening over the 4 conditions, and negative values represent muscle fascicle shortening. What we can see on the left is that the gastrocnemius medialis muscle shortened throughout stance. On the right-hand side, we can see that the total amount of fascicle shortening was significantly reduced in stiffer and stiffest compared to the control condition. On the left-hand side, we have the gastrocnemius medialis muscle fascicle velocity over the stance phase of running for the 4 shoe conditions. And on the right-hand side, we have the average fascicle velocity over stance. On the left, we can see that the fastest fascicle velocity or shortening velocity occurred at the beginning of stance, approximately here. And on the right-hand side, we can see that we found a significant decrease in average fascicle velocity in the stiff, the stiffer, and the stiffest condition compared to the control shoe. We then also compare the total change in fascicle length here on the left-hand side and the average fascicle velocity here on the right-hand side between the control shoe and the best plated condition. The best plated condition was determined as the condition with a carbon fiber plate, which resulted in lowest energy cost of running. And here we saw that both total fascicle shortening and average shortening velocity were significantly reduced when running in the best plated condition compared to the control shoe. Generally, the energy cost of running did not differ between shoe conditions. 2 participants had lowest energy cost in the control shoe, 3 had lowest in the stiff shoe, half the participants had lowest in the stiffer shoe, and 2 had the lowest in the stiffest shoe. There was no significant difference in estimated gastrocmedialis fascicle work between conditions. There was, however, a significant increase in estimated Achilles tendon energy return in the 3 plated conditions compared to the control shoe. To put this a bit into perspective, these 0.15 joules per kilogram correspond roughly to 10 joules for a 70 kilogram runner. And 10 joules are approximately 10% of the total positive lower limb joint work. Running in the stiffest condition would then result in approximately 12.5 joules of estimated Achilles tendon energy return. This is about 25% more than in the control condition, or in terms of total lower limb joint work, it is an increase of about 2.5%. We think that this increase of 2.5% in energy return at the Achilles tendon is quite meaningful. It should be noted, in all fairness, that due to the limitations associated with these energy return estimations, the absolute return values are probably overestimated, but the relative changes in energy return estimates between conditions are not affected by that. The findings of our study show that the function of one of the ankle's plantar flexor muscles, namely the gastrocnemius medialis, can be altered by increasing the midsole bending stiffness of shoes. Specifically, the muscle fascicles shorten less and with a lower average velocity when running in stiffer shoes. The analysis of the ultrasound data showed that the gastrocnemius muscle shortened less in stiffer shoes. The kinematic analysis, however, here on the right-hand side, showed no differences in ankle joint angles, especially no differences at the end of stance at push-off. We therefore deemed it possible that the Achilles tendon may have performed the remaining quote-unquote shortening of the entire muscle tendon unit to maintain similar ankle angles. We think that this then resulted in increased estimated energy return by the Achilles tendon. The fact that the tendon energy return was increased in the stiff condition could have implications for running at distances beyond what we measured in this study. Perhaps this extended energy return would allow the muscle in series to fatigue at a later point during a prolonged run. This could potentially delay a fatigue-induced joint work redistribution from distal to proximal joints. A recently published study investigated soleus fascicle dynamics when running at 3.5 meters per second in footwear of various midsole bending stiffnesses. This study performed by Beck et al. Showed that there were no differences in soleus length changes, illustrated here on the left, and soleus velocity, shown here on the right, between shoe conditions. It is therefore possible that bending stiffness of shoes may have different effects on different muscles. Perhaps this is also the reason why we did not see general differences between conditions in the energy cost of running. Maybe some muscles were affected positively and some muscles negatively, and these effects potentially canceled each other out. Now it would be important to discuss some order of magnitude and to highlight some things that are still unknown. The footwear conditions that we used in our studies do not allow us to make conclusive statements about how the Vaporfly or shoes built in a similar manner work. However, there are some biomechanical and physiological responses that are similar, which may allow us to draw some comparisons. For example, running economy was shown to improve by about 1% when running in shoes with straight carbon fiber plates. Running with a curved plate, however, improved economy by between 2.8 and 4.2% on average. The 1% improvement with straight plates was first shown by Rowan's definition in 2006 and then by Owen Park in 2017. We showed that running economy can be improved by 2% on average if the stiffness is increased to an quote-unquote optimal stiffness when running at 90% of speed at lactate threshold. It has been shown that a percent change in running economy corresponds to approximately 2/3% in performance. Then a 2% change in running economy would correspond to a performance improvement of about 1.3%. On a 2-hour marathon, this would be approximately 95 seconds. Some different responses also need to be highlighted. Stance times, for example, were significantly longer when running in shoes with straight carbon fiber plates. These increases were between 2 to 5% depending on the cited study. When running in the Vaporfly shoes, however, stance times were not significantly different from other conditions that were tested that had no carbon fiber plate. The two studies that repeated the initial running economy study performed by Hochhammer and colleagues have shown that variations in stance time between the Vaporfly and the world record shoe were related to the metabolic improvements. The external moment arm, which again was determined as the perpendicular distance between the ground reaction force vector and a ankle joint center, was shown to be increased when running in shoes with straight carbon fiber plates. The only study that I am aware of that looked at the external moment arm when running in the Vaporfly shoe was performed by Hochhammer et al., following up on their initial running economy study. And in their study, they showed that the moment arm to the ankle joint center was actually decreased during push-off. Irrespective of these different responses in external moment arms, the ankle plantar flexion velocities were reduced by 5 to 9% when running with straight plates and by about 6% when running in the Vaporfly shoe. And these reductions in angular velocities were believed to be related to slower shortening velocities of the ankle plantar flexor muscles, which ultimately was thought to affect the economy of running. So as you can see, there are some similarities, but there are also some differences in how straight and curved carbon fiber plates function. And I think that this is the main characteristic that we still don't understand very well, the geometry of the plate. Specifically, the exact effects of how much the plate is curved and the location of the bending point is not well understood. In summary, increasing the shoe bending stiffness using straight carbon fiber plates redistributed lower limb joint work from the knee to the MTP joint. This could be beneficial for long distance running as more joint work is performed by muscles with a smaller volume. Increased shoe bending stiffness delayed the onset of fatigue-induced lower limb joint work from distal to proximal joints during a prolonged run. This may be beneficial for long distance running as work is being produced for a longer period by muscle tendon units that are believed to be better equipped for storing and returning energy. Also, increased shoe bending stiffness decreased estimated shortening velocities of the shank muscle tendon unit. If these changes are attributed to the muscle, reduced shortening velocities could be related to lower metabolic rates during running. And finally, increasing the bending stiffness of shoes decreased the amount and the average velocity of shortening of the gastroc medialis muscle fascicles and increased estimated Achilles tendon energy return. Slower shortening velocities of the muscle and increased tendon energy return could allow the muscle to fatigue at a later point during a prolonged run. Thank you.
Thank you, Sasha. Before we get the discussion started, I would like to gently encourage you to turn on your web camera if you feel comfortable with it. I'm sure that will allow us to have active interaction during the discussion period. Thank you very much. So if you have any questions to Sasha, please use the raise hand button that can be found if you go click the icon labeled participants at the bottom. You will see the blue icon raise hand button at the bottom on the right-hand side. The floor is now open for the questions and discussion. Yes, Tim, please go ahead. You are muted now. I cannot hear you, sorry.
Right now?
Yeah.
Now I can hear me. Thanks for the presentation, Sasha. Very interesting.
Thanks.
Just wondering, so you did see a difference in the fascicle shortening, but you didn't see a difference in the fascicle work. Does that mean that the fascicle force sort of compensates for the fascicle shortening, so that more fascicle shortening meant less fascicle force?
Yeah, so it could be that either estimated fascicle force was higher, and therefore there was no difference in work, or because stance times were longer in the stiff condition, and therefore you take the integral over a longer time period, right, of force and length. So you may have, maybe that's the reason why, either the force or because the stance times were longer.
Yeah, this was sort of my second question, is that I would expect forces, average forces, to be smaller if you have longer stance times. Do you agree with that?
I think so. Well, at least there is a good body of literature that would suggest that, or at least that you would have a reduced activation with a prolonged stance with prolonged stance times. Yeah.
So that, of course, doesn't have to mean that the muscle force is also affected by that because of the gear ratio, what you talked about. So maybe that could explain that the fascicle force would be smaller for stiffer shoes. I was just wondering, and normally, if force would be constant, then you would expect the fascicle work to be affected if fascicle shortening is affected.
Yes, correct.
Sorry.
Yeah. But when we estimated the, first the Achilles tendon force, and then we basically just scaled the Achilles tendon force based on the cross-sectional area of the gastroc compared to the other plantar flexor muscles. Because there was no difference in ankle joint moments, there was no difference in estimated Achilles tendon force, and then there was also no difference in estimated gastroc fascicle forces, but the differences were I guess still not picked up in the work calculations, perhaps due to the prolonged stance times.
I see. And okay, last question is the effect of stance time. So increasing stance time reduces the cost, apparently. What's your take on that, in terms of underlying mechanisms? I think you just said that you think activation plays a part.
Yeah, so based on the cost of generating force hypothesis, you would expect to, if you have shorter stance times, you'd be taking more steps, and therefore you would probably be engaging faster muscles, and this would cost more energy to do. But we obviously, if you extend stance times infinitely, you're not going to move anywhere, so that's not going to work. It's not going to be going well. So I think that if you increase stance times to a certain degree, it's probably going to be good. But then if you extend it just for too long, it's not gonna work beneficially for you anymore.
Yeah. Okay. Thank you.
Okay, Arash, please go ahead.
Great presentation, Sasha.
Thanks, Arash.
So I have just a couple of questions. First one is when you looked at this MTP joint work in the first study, there was a huge standard deviation in the stiffer shoe condition compared to the control one, if I'm not mistaken.
Let me just go back to the graph. This one?
Yeah.
Yeah.
So why do you think is that?
So the reason for it most likely is because because the stiff condition differed between participants, right? We had for seven runners, the stiff condition was 4 times stiffer than the control, and for 8 runners, the stiff condition was 8 times stiffer than the control. So once we pooled them, this is probably the reason why we have this high standard deviation. Because let's take the 7 runners who ran in the stiff condition that was 4 times stiffer than control. They were maybe somewhere around here, whereas the runners who ran in the stiff condition that was 8 times stiffer than the control, they were probably somewhere here. And then if you pull them together, you get somewhere in between here. And probably that's why the standard deviation was so much higher.
And maybe that's why the results wasn't significant for the stiffer condition.
For the MTP
because
joint,
you can kind of see that trend that it's going, the positive work is getting smaller at the end.
Agreed. Yeah, it's definitely possible. It also plays a big role what correction you perform or what correction you use for these multiple comparisons. Here we use the Bonferroni correction just to be quite conservative. And you know, when you use the Bonferroni correction, these significant differences that you might pick up with other correction methods get lost. But irrespective of the correction method we used, it always was that there were more significant differences in the control condition than in the stiff condition, and they occurred much earlier during the 10-kilometer run in the control than they did in the stiff condition.
Okay. And then in the second study, so the cost of running numbers seem to be very high compared to for like a trained runner, 44-minute 10K runner. Cost of running usually for average people is around like 4 joule per kilogram per meter. And in here, we see an average of 4.5, 4.6. Is that a reason for that? Is there a reason for it?
You mean these values here?
Yes.
So potential, it could maybe be that they were running at 90% of like the threshold. So it's a quite intense speed. That's my best guess.
Mm-hmm.
I mean, when we had initially the energy cost of running in kilocalories per kilogram per meter, and there the values were very comparable to different studies that I've seen.
Mm-hmm. Yeah, but that was just interesting to me that considering these runners are trained, these numbers look really high. Like, I mean, like maybe like I was expecting 3.8, 3.9 or something. Okay. Yeah, interesting. Thanks.
Thank you.
Brent, please go ahead.
Yeah, nice talk, Sasha.
Thanks, Brent.
Quick shout out to some old school HPLers on the line. I see Chris Lamsky even. I think.
Oh God.
Okay. So Sasha, the fascicle shortening differences were on the order of maybe 1-2 millimeters, maybe a little more. I'm not really sure, but that's probably about the thickness of the inserts that you're using, 1-2 millimeters. So I'm wondering what role, if any, you think just having an insert in there, just anything that lifts the heel up 2 millimeters, how that might influence the fascicle shortening. Did you hear me?
Yeah, I did. Sorry, I'm just thinking. Well, but the probe itself didn't change, right? The location of the probe on the muscle didn't change. And so only because they're lifted up by 2 millimeters, I don't I don't know how that would be or why that would affect the shortening itself.
Okay. Yeah, I don't know. I just, you're talking about maybe like these things like gear ratios and whatnot, if that would have any influence on the external moment that the ankle would need to overcome or anything. I mean, it's really subtle, but then the changes that you see in Achilles are very subtle. The next question is maybe not such a question, but it's more of a comment in reference to this gear ratio thing. So gear ratio, I think it makes sense when you start talking about it at the ankle, the Achilles tendon, the moment that it needs to overcome. But I'm really puzzled why then somebody like Stefan Wilmacher would try to look at this thing at places like the knee and the hip. I mean, I could calculate a gear ratio with the ground reaction forces with the forces in the neck, with the muscles in the neck. But it's not like my neck muscles would have to overcome that moment, right? So what is the rationale with calculating a gear ratio at the knee or at the hip?
Yeah, to be honest, I don't know why the gear ratio was calculated at knee and the hip. I agree that this is a bit puzzling, as you said. I remember reading in David Winter's book something very similar where he was describing of how, I think he also brought up the neck example, how this may not necessarily be a valid method to estimate what the internal load would be.
I'm sure I probably pulled that from Winter's book too. That's
okay.
Okay. All right. I just didn't know if people were doing that.
Yeah.
Okay. Thanks.
Okay, Michael, please go ahead.
Hey, Sasha. That was a nice talk.
Thank you, Max.
I know we've talked about this a lot, so it could be that I've already asked you these questions. But do you have any ideas to what the effect of running speed is on the kind of the preferred plate, or how the plate kind of redistributes work? Like, is it people who run faster benefit more from stiffer shoes?
Yeah, so I'm aware of two studies that looked into that, and they were published basically a few days one after the other. One from Ian Hunter's group, and then one by Evan Day and Mike Hahn. And both suggest that the quote unquote optimal stiffness is related to running speed. So if you, as you said, if you run faster, you would need a stiffer shoe. But specifically the study by Hunter et al., for example, they fit a second order polynomial to their metabolic data, which has been done many times before. And that was done at two different speeds. But then if you rank the shoe conditions from best to worst, like the order of shoe conditions was the same for the top 4 conditions, I think it was. The order of conditions was the same between the two running speeds. Now the second order polynomial had its minimums, so its optimal condition at a different point somewhere, but the order of conditions was the same, tested experimentally. So I think it wouldn't surprise me if the optimal stiffness was speed related, but I don't think that there's currently enough evidence to say so indefinitely.
Yeah, that's fair. And second question, does the person's running speed change when the work begins to redistribute? Like, is it, in people who are run faster, is it harder for them to maintain kind of that distribution for as long as at a slower speed?
Well, I don't know how it would be in a real life scenario during a race. I doubt that someone who is running competitively at a competition is running at a constant speed as the participants were doing here in our studies. Because people were running on the treadmill, the speed was constant throughout the entire session. So I can't really answer if speed would change.
Yeah, that's okay. And then my last question, were there any changes to step length across the prolonged run, which could also explain some of the changes to joint work?
I don't know. I have not looked into that.
Okay.
I'll have a look.
You don't need to. I mean, it's just a possibility because the
Yeah.
changes are similar as to what you would expect if step length begins to shorten too. Like you have a reduction in knee positive work with no change in ankle work.
Mm-hmm.
So
I can't remember if in the Sano paper, for example, if they reported any distance effects on step length.
mm-hmm.
But I know from our first redistribution study where we just had people run for 30 seconds, there was no difference in step length between shoe conditions. So there may be a distance effect, but I don't think there is a shoe effect.
Mm-hmm. Okay, thanks.
Okay, Art, please go ahead.
Yeah, I'm just curious what your opinion is of what we would like to see happen that explains the effect of the midsole stiffness on say running performance or energy cost. And I think it's especially interesting that you saw an increase in the Achilles tendon energy return. But what do you think is best? So I'm just going to ask you your opinion on some things. First of all, do you think elastic energy return is important for running? And then given somebody running, say in these kinds of conditions, do you prefer higher energy return or lower energy return? And then, and also if there's any measure that you think is really a good indicator of energy cost, other than that, what do you think that would be?
Okay, so I think the first question was what I would expect, right? Whether to see more or less energy return. Was that the first?
Well,
part?
it doesn't even have to be expectation. Just what do you prefer? Like, what do you believe in?
Well, I thought initially that the network performed at the muscle tendon unit would be the same. So there would not be a difference between shoe conditions. So that means if you have now more Achilles tendon energy return, that we would see a decrease in muscle work just to keep the numbers the same. But that wasn't the case, as we've seen in the mechanical work performed at the ankle joint. In the stiffer condition, for example, there was more total positive work performed at the ankle joint compared to the control condition. So instead of the muscle decreasing its work, the fact that there was more Achilles tendon energy return just increased the total amount of work performed. That is something I think we didn't expect. And I think what would be better is if you do decrease the muscle work and increase the tendon energy return instead. I think that would be better.
Okay, and then how do you expect the MTP stiffness to affect Achilles tendon energy return?
The MTP stiffness or just the
the
carbon fiber plate?
Say
okay.
Yeah, sure.
Yeah. Well, I think it's affected by the fact that the MTP joint dorsiflexes less or is less extended, and therefore the center of pressure moves further anteriorly, which increases the moment arm to the ankle joint center. And we get back to the gear ratio topic again, where with a relatively constant internal moment arm, you now have a greater external moment that you need to overcome with your internal muscle tendon unit force.
And I guess I was a little bit confused. I thought the gear ratio results were not super clear on having that effect.
Well, the gear ratio results from previous studies, for example, by Carrier from '94, they show that the shortening velocities of the ankle plantar flexor muscle tendon unit, that these velocities would be increased if you would have a gear ratio that was, first of all, fixed that wouldn't change, that was constant during the stance phase. And second of all, if that gear ratio was smaller than what you observe typically during regular running. And then if you would have higher velocities, this was speculated to be energetically more costly.
Okay, and then based on what you've done, do you agree with that?
Well, we did see reduced shortening velocities, both in our estimation of the shank muscle tendon unit and in the gastroc medialis fascicles. But then the differences were not large enough, I guess, to cause changes in whole body energetic cost. So I think we may have affected, quote unquote, positively the gastric muscle, but maybe some other muscles were not affected positively.
And it seems like you got a pretty substantial benefit here from your midsoles. So I just calculated this, and to me, it looks like you got almost 2%, which seems pretty good. So do you consider that within the range of what people did previously? Because I think you had a slide showing 1%, or do you think there was something like that was a little bit better here?
Okay, so yeah, typically, or like previous studies that used straight carbon fiber plates, for example, Rowan's definition or Owen Park, they reported differences of about 1%. When we compared the control condition to the best stiff condition, so
stiffer,
one of these three conditions, depending on, because it was different for each participant, there we saw a average improvement of 2% in running economy. Yeah. And that is, I think that is quite substantial, because that would correspond to approximately 1.33% in performance. And that would be over a 2-hour marathon, that would be about 95 seconds. Which is quite unheard of. Except for, I think, Paula Radcliffe, she broke her own marathon record by more than 95 seconds.
Right. So my question though is this within the noise of just doing experiments, or do you think that you have beat Darren's definition?
No, I don't think I have beaten Darren's definition. I think there were other methodological differences between Darren's study or Suk-Young Park's study and our study. The fact that we had people run at a relative intensity, I think, may have played a big role compared to having everyone run at a fixed speed, which for some people may be more exhausting and for some other people less exhausting. And then with respect to the noise of measurement, we did determine the smallest worthwhile change from our metabolic data. And we saw that, so the smallest worthwhile change in our data set was 0.95% in running economy, and 9 out of the 14 participants had changes greater than the smallest worthwhile change. So I would argue it's not just noise. I know, yeah.
Okay. Well, just as a suggestion, I think, well, first of all, a 1% improvement is already a huge deal. That's enormous. And then if you have the possibility of a 2% change, that is also enormous. And then I just feel like that's something worth talking about here, just as a purely kind of tantalizing result.
Mm-hmm.
Okay, thanks.
Thank you.
Philip, please go ahead.
So you mainly presented results on male athletes. Do the same results also hold for female athletes?
I don't know. The reason why we had male athletes was purely because of convenience, because we had shoe sizes in between size 9 and size 11. And that was the only reason why we had tested male runners. I don't think there would be a difference between male and female runners. I think every muscle functions basically the same, and therefore I don't think there would be a difference, any sex differences. I think there is still an optimal bending stiffness for men as for males and for females. I don't think there are any general sex differences, I think, but that's just a guess.
So is then the main body of literature like really largely focused on male athletes?
The main body of literature on this topic has predominantly been done on male runners, yes. And I assume that this was mainly done out of convenience.
Yeah. Okay, thanks.
Thank you.
Rob, if you have any final question, please go ahead.
Sasha, that was just a fabulous presentation. That's a lot of work, and I'm really impressed and delighted to see it. So thank you very much and congratulations.
Thank you.
I've got a few points where I might have made an error in what I was picking up. So with an increased stiffness in the shoe, there was less shortening of the fascicle. So that's fine. I think you said that there was no change in joint angle. And
Correct.
so if that was the case, then the length change in the gastroc would be taken up with a greater length change in the Achilles tendon. In order to have more stretch of the Achilles tendon, you'd have to have more force. And there's also, if there's increased Achilles tendon energy return, I would again think you would have to have stretched it further and you would have to have more force, which would be, if there was more force, would be consistent with less shortening of the fascicle. So I've got a circular argument. So if the increased stiffness in the shoe is leading to more force in the gastrocnemius, more stretch of the Achilles tendon, and you're talking about marathons and 10-kilometer runs, are we also talking about a higher likelihood of Achilles tendon injury? Because throughout those step cycles, you've got perhaps the same number of cycles, but a higher force. And so could the benefit in performance, but are we actually going to, putting this into a shoe, is it going to make it potentially more injurious to the tendon?
I don't know the answer to the question. I would have to speculate. I would say there is potentially a higher risk of Achilles tendon injuries if you're stretching the tendon more by applying a greater force to it. Yeah, but I don't know this. I don't know this for sure.
Because I think if this is looking at putting such a device into a commercial shoe, then it's, I mean, we have plenty of these presentations saying that the likelihood of rupture goes up as the number of repetitions and the force goes up. So if you, it raises because the other alternative is a human's still evolving in terms of running, and we haven't made a stiffer region of the foot, or is it because if we did that, we break our Achilles tendons, which is purely speculative.
Yes, yeah.
I may step in quickly. There is some anecdotal evidence when we started working with Adidas with these plates, that they told us that they had athletes, an increased number of athletes that had Achilles tendon problems with these plates. So, but it's only anecdotal.
Yeah. But a lovely presentation. Thank you.
Thank you. Thank you.
Okay, on that note, I would like to thank Sasha again for sharing his great work and great presentation. As I still see some people have more questions, so I can just stay a bit longer. So if you have more questions, then maybe you can ask a question afterwards. Next week, we will be hearing from Arash Kasetrash, and the title of his talk is Neuromuscular, Biomechanical, and Energetic Adjustments Following Repeated Bouts of Downhill Running. Thanks for coming today, and I'll see you all next week.